It's recording! Ladies and gentlemen, welcome to a new video by Tukoe. Amazing. Is that gonna be intro? Probably not. Anyway. It's the usual. I'm making a video. That means there's gonna be a test. The test is tomorrow. What is it about? It's about... Hold on, let me get the pen. It's about... Thermal... Oh, that's A. Thermal... Physics. Yay! Hooray! Amazing. And my teacher sent me the quote-unquote syllabus, I guess. It's gonna be on converting the heat, like Celsius to Kelvin, Kelvin to Celsius, Celsius to Fahrenheit, Fahrenheit to Celsius, reamur, etc., etc. Calories, and then Black's principle. That's it. That's black. No, that's red. The writing is black. No, the writing says black. Yes, Black's principle. Thermal expansion. Thermal expansion. In last but not least is heat transfer. Hooray! And I'm gonna try to explain everything here. And I have like notes on the side here to help me try to explain. So yeah, basically. Let us begin. Woo! Thermal physics. Sorry. Anyways, let's start with converting. But first, we need to know what the hell are we talking about right now? Well, we're talking about temperature. Converting temperature. Temperature. There's a lot. Actually, no. There's 4 that I know. In the U.S., in the country of USA, they use Fahrenheit, which is F. In science, they use C, which is Celsius. Wait. No, sorry. Fahrenheit is in the US. Celsius is everywhere else except the US because I don't know. Everywhere else. And in science, there you go. In science, it's Kelvin. Banger. And last but not least is reamur. I don't know. It's not even in my notes. I just know this. And Celsius, this is based off of water. This thing is based off of water. That's water. Where 0 Celsius is the freezing point, where water freezes, and 100 Celsius is the boiling point, where water boils. Yep, that's cool. These are the temperature scales, I would say. Yes, the scales. Temperature scales. Now, how the hell do you convert them? I have to Google reamur because it's not in my notes, but for Fahrenheit, Fahrenheit to Kelvin, it is simply the heat in Fahrenheit is equals to 9/5 multiplied by the heat. Wait, Kelvin? No, sorry, Celsius. Heat in Celsius plus 32. So the heat in Fahrenheit is equals to 9/5 multiplied by the heat in Celsius plus 32. Let's say this is -10. The heat in Celsius. It's -10 Celsius. So it would be this 9/5 -10 plus 32. You can cross this out. This becomes -2. This becomes 18. Sorry, -18. Oh, what the hell? Sorry. This becomes -18. Yes, plus 32, which is equals to what is it equal to? 14? Okay, let me verify that. Hold on. -10 Celsius to Fahrenheit. It is in fact 14 Fahrenheit. Let's go. And if you want to do Celsius to Fahrenheit, Well, it's basically the opposite, right? But okay, so you move the 32 here. Hold on, let's. So you just gotta memorize this one. Let me show you. TF 9/5 TC plus 32. And now we solve for TC. So we get TF minus 32 plus 2 9/5 TC. So TC, heat in Celsius, is equals to 5/9 multiplied by TF minus 32. See? You only need to memorize one of them. Just memorize one of them. Look. Let's try this. Let's go 72 Fahrenheit. How many Celsius is that? Okay. So we're gonna put 5/9 multiplied by 72 minus 32. This would equal to 40. Right? Yeah. 5/9 multiplied by 40. I mean, I guess, bro, like it's 200/9. How much is that? Hold on. Let me use a calculator. I don't like this number. 22.2. Now let's Google it for confirmation. 72 Fahrenheit to Celsius is 22.2. Yeah, 22.2. Woo! Boom. We already done Fahrenheit. Now let's move on to Kelvin. And Kelvin is the easiest one so far. How do you do that? Well, it's easy. To do Kelvin to Celsius, you simply the heat in Kelvin is equals to the heat in Celsius plus 273. That's it. Very easy, very simple. So how do you do that? How do you do Celsius to Kelvin? Well, it's easy. TC is equals to TK minus 273. It's so easy. It's so simple. It's so shrimple. Now for reamur, I don't know. Let's see, reamur to Celsius. What in the great heaven is this? Wait. Oh wait, this isn't that bad actually. Hold on. Yeah, this isn't too bad. Never mind. So reamur to Celsius, the heat in the reamur is equals to 4/5 multiplied by the heat in Celsius, and the heat in Celsius is equals to 5/4 multiplied by the heat in reamur. Okay, hold on guys. I have returned. Alright, it's pretty easy as well compared to this. What the hell? 9/5 TC 32. What? No, thank you. So let's see here. Well, let's say I have 20 Celsius. Wait, no. Actually, yeah, 20 Celsius. How many reamur is that? Well, let's see. TR is equals to 4/5 and it's 20 Celsius. This becomes 4, so it's 16. 16 degrees reamur. Let's check. 20 Celsius to reamur. Or reamur, I don't know how to pronounce it. It's 16! Yes, sir! And that's all of the temperature scales, really. Yeah, that's cool. But what, hypothetically speaking, you want to make something up. What do you do? Well, here's something you can do. Imagine we have this thing. A thermometer. Yes. Thermometer. I don't know what it measures. It just measures the temperature. And we have another thermometer, which measures temperature, but on a different scale. Yes. And let's say we have. Wait. we put this thing in water. We're gonna put it in some water, something, and then it's gonna show TA. And then we put it in something else, which is colder. It's gonna go to TB. And then you go, oh, okay, that's pretty cool, I think. Oh, but the next thing is gonna be really cool. So you put this thing, right? You put this thing, different scale. You put it in the same water as the A1, and then you'll get TA. It's not TA, TAX. Let's say it. Tax. Tax. Yeah, tax. TAX for the different scale. And then you put it in the B water, and it's like, oh, okay, this is TBX according to us. Now, let's say this is T, and this is TX. How can we find this? Well, it's simple. The ratio between this and this is the same as the ratio between this and this. How do you write it? Well, it's basically T minus TB divided by TA minus TB is equals to TX minus TAX divided by, wait, not TAX, TBX, sorry. It's TBX. That's a B. TAX minus TBX. Alright. Yes. Yes. Let's try this. Let's say we know what's going on, okay? So let's say this is Celsius and this is Kelvin. And I'm gonna put TB as 0 Celsius. 0 Celsius. This as 100. This one is 273. This one is 373. And let's say when this is 20 Celsius, how much is this? Well, we know it's basically 20 plus 273, but let's say we don't know that. Let's say we want to use this one. Well, basically, we put T, we know T, that's 20, minus TB, which is 0, divided by 100, which is TA, minus TB, which is 0. This is equals to TX, the one we're looking for. Basically, if it's 20 Celsius, how many Kelvin is that? Minus TBX, which is 273, divided by 373, which is TAX, minus 273. This becomes 20 over 100, equal to TX minus 273 over 100. You can cross this out. 20 is equals to TX minus 273. Therefore, TX is equals to 273 plus 20, which makes it 293. Wow! Banger! Okay, hold on. I have a... Wait, actually, we're gonna put all of the practice questions into the last part. Yes, the teacher gave us 45 practice questions, and I'm gonna do all of them in one sitting. Alright, banger. Now, we've done temperature, and everything in conversions, and yada yada yada, everything's cool. Oh god, I'm kinda thirsty. Wait, I'm gonna grab a drink, hold on. Alright, I'm back. I got a drink of water. Let's go. Alright, we finished talking about temperature. Temperature. Check. Oh my god, my writing is horrible. Temperature, done. But now, we know what temperature is, but what's heat? What's the difference between temperature and heat? Well, it's easy. Wait, hold on. I see. Okay. Anyway. Well, I mean, okay, temperature versus heat. What the hell's the difference? Well, let's look at the units of them, alright? Temperature, we know it's Celsius, Kelvin, reamur, Fahrenheit, right? But heat is in joules? Calories? Whoa, 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 hold on, wait. To all of you, to all the boys out there, you might know that joules is also energy. In mechanics, you know, half mv squared, that's in joules. Mgh, that's in joules. Negative k, half kx squared, that's in joules. So what does this mean? This means heat. Heat is energy. Temperature is how hot something is. Heat is how much energy that thing has. The more heat that a substance has, that means, hold on, wait. If the heat is high, then the substances is moving faster, more moves. If the heat is up, more moves. Why? Basically, the theory is that heat is basically just kinetic energy, but it's the kinetic energy of the molecules. So the molecules are actually moving, and that's what's causing the heat to exist. It's basically moving atoms. The atoms are vibrating. Oh, yeah, they're vibrating. Whoa. And the vibrating is kinetic energy, and the kinetic energy is heat. Yeah, so heat is energy. Cool. Anyway, so I should mention. Actually, no, I'll mention it later. It's in my notes. Yeah, exactly. Anyway, definitions. Let's read my notes. Heat is defined as the transfer of energy across the boundary of a system due to a temperature difference between the systems and its surroundings. What? Okay, what about this? Heat is energy transfer due to difference in temperature. Yes, correct. Also, by the way, temperature and heat, they're proportional. If the temperature is big, the heat is big. If the temperature is small, the heat is small. Wait, heat big, therefore temperature big. Temperature. Yes, okay. Banger! Alright, banger. Anyway, heat. Let's move on to heat now. Heat. We know, what was it? The units of heat. Calorie and joule. 1 calorie is defined as the energy needed to raise the temperature of 1 gram of water by 1 Celsius. 1 calorie is energy needed to increase 1 gram of water 1 gram of water by 1 Celsius. Yes. And joule is 4 times 4.2 of that. So 1 joule is equals to 4.2 calories. Boom, that's for your conversions. Banger. Excuse me. Alright, that's all in heat. What else do we need to talk about? Calories. That's calories. Black's principle. Oh, okay. There's this thing we call heat capacity, which is big C. capital C, heat capacity. Heat capacity is basically how much energy you need to raise something by 1 Celsius. Yes, yeah, that's it. So basically, oh, let's say the heat capacity is 20. That means you're gonna need 20 joules or calories to raise a substance by 1 Celsius. And there's also this, a smaller c. I'm gonna add like, I don't know, what should I add to make this different? You know, I'm gonna add a boom, a more curly one. This is heat capacity. This is specific heat. You don't have to write it like this. I just want to write it like this because why not? So I can tell the difference. By specific heat is basically heat capacity per unit mass. Specific heat is equals to the heat capacity divided by the mass. Yeah, that's it. Cool. Now, we did say that, wait, where is it? Yeah, heat is equals to the energy transfer due to difference in temperature. Well, we can actually calculate how much energy is currently being transferred due to temperature changes. We call it Q. This is the energy being transferred. Q is equals to M C delta T. Delta T. Alright. Now mass C delta T. All of these could have different units. We have to make sure we're using the right one. Okay? Let's see in the case of water. Okay? In the case of water, the specific heat of water is equals to 1 calorie per gram Celsius degrees. So this is for water. You see it's 1 calorie over gram per Celsius degrees. So wait, sorry, degrees Celsius, not Celsius degrees. Sorry. Yeah, it's 1 calorie over gram per degree Celsius. Per gram degree Celsius. Which means if I'm using 1 here for water, that means for the mass I need to use grams, and for the difference in temperatures I need to use Celsius. And then the result will be in calories. But we can also use this for water, but this would be in joules. Gram Celsius. This is the same thing, but the result will be in joules. But you can also say, oh, wait, but what about 1,000 kilocalories? But this time it would be kilograms. So yeah, there's a lot of differences here that we need to pay attention to, because we need to look at the units. The units are really important, you guys. We need to pay attention to the units. But basically, this is the main idea. And for water, we mainly use this. Pay attention to the units. The units are very important. You need to look at the units, because the units change everything. But you might ask, oh, but hold on. What if I don't know the change of temperature? Well, you can also use this. You remember that C, the heat capacity, is equals to, wait, no, the specific heat is equals to the ratio between the heat capacity and the mass. So yeah, let's put that in. Q is equals to M. C is the ratio between the heat capacity divided by its mass. Delta T, boom, boom. So we'll get Q is equals to the heat capacity of a substance multiplied by the change in temperature. Boom. Now we have two equations. One with heat capacity and another with specific heat. Now, before I go on, I need to mention one thing. Change of matter. Hold on, let me make a graph. Whoop, whoop. This would be in temperature, which is in Celsius. And this one would be, I don't know, energy, I guess. I'm looking at my notes, it says energy. Basically, this would be 0, and let's say this is 100. Well, actually, no, I want to put 0 here. It's like negative something. Now, at this point, let's see here. We're gonna add energy. Let's say it's water, okay? So below 0, it's ice, cold as ice. I'm gonna add some energy to it. Whoop. You would expect it to keep going up, right? But no, it does not keep going up. Why? Why is this? Basically, let me show you. Imagine this is water, so it's below 0, which means it has to be frozen. If I add more energy to it, it's gonna start raising in temperature. And then at 0, it's gonna stop. It's gonna go horizontal a little bit. and then it's gonna go up again, and then at 100 it's gonna stop again, and then it's gonna go up again. What's going on? Basically, we have two parts here that doesn't seem to want to move. These two parts. So what's going on here? Basically, at these two parts, the heat is not being used to change the temperature, but it's being used to change the state. At this point, everything is ice. But at this point, all of the ice is slowly being turned into water. So, not necessarily the temperature is not necessarily going up, but the more you add the energy, the more ice is going to turn into water. So this is basically the melting point. We call it fusion, I think. I'm pretty sure it's fusion, because I'll say why later. And this is the point where everything is water, so it's gonna go up again. And then here, this is where the water turns into a gas. The liquid turns into a gas. We call it evaporation, because you evaporate. Yeah, yes, sir. Now, how do we do this? What do you do? Because here, if you want to calculate the energy, the heat here, well, you can simply put mc multiplied by delta T. But delta T means the change in temperature. And here, there's no changes in temperature at all. The temperature is constant at these points. So what do we do? Well, we have one more equation, which is Q is equals to mL. This is the last one. What is L? Well, there's two. The first one is latent heat of fusion. Latent heat of fusion is basically the number for when the ice turns into a water, and there's latent heat of evaporation, which is the number that's used to turn the water into a gas. Yes, and the unit is joule per mass. Wait, energy per mass. Yeah, that's it. Yeah, remember all of these two, guys. Q equals mc delta T, Q equals C, big C, times delta T, and Q equals m times L. And keep in mind, pay attention to the units. The units are really important, guys. It's really important. Alright, what is next? Black's principle. Okay, Black's principle. Alright, everything is starting to get a little bit more difficult. But I'm gonna talk about theory from here, and then later on, we're gonna talk about everything questions. It's gonna be 45 questions. I don't know if I'm gonna do all of them, but yeah, Black's principle. Basically, a really smart guy once said, wait a minute, if an object is giving heat to a certain object, then the other object will receive that heat. You might be thinking, well, yeah, duh, what do you think? But this is actually really revolutionary, which means the sum of the heat that is transferred is equals to the sum of the heat absorbed. And yeah, that's basically it. This is all the theory you need to solve thermal equilibrium questions. This is everything you need. We can go into a simple question now. Okay, just a simple one. Okay, let's see. Let's say I have water. That's water. The water is 100 grams and is currently at, let's say, 50 Celsius. And then this, let's call water A. And then I have another water B. I have actually 500 grams of it. And its heat is at 10 Celsius. Now your teacher might ask you, oh, what is the thermal equilibrium, or what is the equilibrium? Yeah, at what heat does it stop exchanging exchanging Q's, exchanging the heat? When does it stop? What's the point where the temperature is the same? Yeah, there you go. Okay, We use this Black's principle. So Q. Okay, wait, hold on. Let's do a checklist. We know the mass. Okay, of course we have to know the mass. No, we don't. We can't. But we know we don't know the specific heat. So we know the mass. So it's either this one or this one. And then we have C. Do we have C? We don't. They don't tell us what the C is. But I did say this is water, which means the C is equals to 1. So we do know the C. And what about T? The T is what we're looking for. So we have everything. Okay. So let's rewrite everything. Q transferred is equals to the Q absorbed. Alright, so what's Q? This is the mass MA. This is C, which is 1, and this is delta T, and this is equals to this one. MB C delta T. Alright, but what's the delta T? Well, imagine it like this. We have one water which is at 50 and another at 10. To reach thermal equilibrium, this has to go down and this has to go up, which meets at T. Oh yeah, heat goes from hot to cold. Obviously, this is T. So the delta T on this one with the 50 Celsius, it would be MA. So hold on, 100 multiplied by 1 multiplied by 50 minus T. Because it's going down, right? So 50 minus T. And then this one is going to be 500 multiplied by 1 multiplied by T minus 10. T minus 10. So we put the bigger one first and then the smaller one next. Easy. Alright. So this, we can cross this out. This will become 50 minus T equals to 5T minus 10. Minus 50 actually, sorry. I'm going to move this here. And then we can move the 50 here and the T here, which means we'll get 100 equals to 6T, which means the final temperature would be 100 over 6 Celsius, degrees Celsius. Or how much is that? Hold on, let me pull up a calculator. 16.7. Oh, 6! Sorry. Around 16.7 degrees Celsius. Nice! Alright, so we know how to kinda use it. Sorry. Alright, that's Black's principle. Very nice, very simple. Alright, what's next? Thermal expansion. Okay, thermal expansion. Hold on, let me check my notes. Alright. Thermal expansion. Okay. Fun fact. Where's my pen? Oh, there it is. Thermal expansion. Thermal expansion. What the hell does that mean? Hold on, let me take a drink. Well, basically, remember when I said bigger heat equals bigger moving? Like the molecules are moving faster and faster? Where is it? Here it is. Bigger heat equals bigger moves. Well, yeah. Bigger moves would mean that it would expand. It would knock the other molecules to the outside more, which means the molecules from like a very dense state, it would turn into something like this, which means it's gonna expand. This is why that objects that are currently receiving energy, receiving heat, they will experience thermal expansion. They will become bigger. But by how much? That's the question. So, thermal expansion happens in 3 dimensions. The first dimension, the second dimension, and the third dimension. Wow, really? No way, I didn't expect that. This is linear, area, and volume. Easy. So how much? Let's see. So the length being added is equals to, wait, yeah, is equals to L null plus alpha, wait, no, not plus alpha, multiplied by, sorry, excuse me, L null, which is the original length, multiplied by alpha, multiplied by the change in temperature. Wait. Yeah, this is the length added. But the final length would be the length added plus L null, and then we know L, the length currently being added. That's just this one. Easy. All right, that's it. We just you really just need to memorize this because the other one is very simple. It's very similar to, for the second dimension, instead of length, it's area. Is equals to the original area multiplied by beta multiplied by the change in temperature, and well, the final area will be a plus a null. And for the third dimension, guess what? It's volume. Whoa, no way. Yeah, I can't believe it. Plus, not plus. Oh my god. It's gamma multiplied by gamma multiplied by the change in temperature, and the final volume is V plus V null. See, it's all very similar. But keep in mind, alpha, beta, and gamma are three different numbers. Three different variables. They're not the same, they're very different. So, if the question says, I forgot what A is. Alpha is like, is the linear thermal expansion coefficient. If it says linear, then it's alpha. You can't use the linear one and the 2D one. You need beta for that. So how do we do that? Well, beta is actually equal to 2 times alpha, and gamma is actually equals to 3 times alpha. Yeah, that's all you need to know. Just keep in mind for that one. Be careful, guys. Anyway, wait, where's my? I'm gonna take a drink. Hold on. Refreshing. Anyway, next. What's next? That's all in thermal expansion. We're gonna check out the questions. Heat transfer. I don't think I'm gonna talk about all of the questions though. Maybe some of it, but not all of it. I'm really tempted to do all of it though. Heat transfer. Actually, I think I'm gonna upload a different video of me just doing the questions. Yeah, that would be cool. Yeah. Anyway, heat transfer. What the hell is heat transfer? So yeah, we already mentioned that. Here's the heat transfer. So it's equals to the mc delta t. But by how much? How fast is the heat currently being transferred? We don't know that. So there's more equations. Yay! Anyways, first we need to know how can heat get transferred. There are three ways that heat can be transferred: conduction, convection, and radiation. Let's start with conduction. Conduction is basically the heat transferred from contact. So if you have two metal plates touching each other, let's call it plate A and plate B, they're touching each other, the heat transfer is currently done by conduction, not convection, not radiation, but conduction. Alright, that's conduction. Or in more advanced languages, when heat is transferred via conduction, the substance itself does not flow. Rather, heat is transferred internally by vibrations of atoms. What? Basically, remember when I said heat is basically moving particles? Yeah, the moving particles in A causes the B to move particles as well. That's how the heat gets transferred by the particles moving each other. That's how. Very cool. Convection is basically by fluids. Heat transfer in fluids generally takes place via convection. Oh, okay. In convection fluids, usually in air. Remember when I said that bigger heat would mean bigger room, which expands, thermal expansion? Yeah, this happens too in fluids. So here, if an air is hotter than a specific air, let's say air A and air B. Air A is hotter than air B. But the hotter would mean it's currently experiencing experiencing thermal expansion. And if you remember, in density is equals to mass over volume. A higher volume would mean a lower density, and a lower density would mean the A substance would float up. Meanwhile, the B substance would go down. That's just a really cool fun fact, guys. And radiation, it's currently, the heat is getting transferred by waves. EM waves. What are EM waves? I don't know. I'm not sure. We talk about this later. EM waves. Basically, it's like they don't need a medium to travel through. It can just travel through anything. Like light. Light is technically an EM wave. And every EM waves travel at the same speed of light. That's like literally that. That's literally an EM wave. Electromagnetic waves. Actually, yeah. And how do you calculate it? Well, it's quite easy, really. Let's use P. P would be power. Power! Power is equals to the heat transferred every second. Alright? Alright. It doesn't have to be second. It's usually second, though. So, in conduction, the power is equals to the coefficient of conductivity multiplied by the cross-sectional area multiplied by the difference in temperature divided by the length. The length of the thing in contact, the length, like how long is that? Yes, that's conduction. And for convection, it is HA delta T. H does not mean height, but what does it mean? Let's see. Convection HA delta T. Newton? What? Really? Oh, that's another. Okay, K is the conductivity coefficient. This is the convection coefficient. Yeah, it's another coefficient, guys, not height. And from radiation, it is equals to sigma A, which is area, the surface area, because it's usually like, okay, what I mean by surface area, radiation is usually like something, let's see, a ball, and the ball is currently radiating stuff. You might be thinking, wait, a ball radiating stuff? The sun. Yeah, the sun is radiating light rays to us. That's why we feel hot when we're outside, when the sun is very bright. That's why we feel hot. We're currently experiencing radiation from the sun. Multiplied by E, or epsilon, I guess, multiplied by T to the power of 4. Sigma. This is the Boltzmann constant of radiation. What is it equal to? Hold on. I need to Google this one. Boltzmann constant of radiation. It is, oh my god, 5.67 multiplied by 10 to the power of negative 8. A is, well, as I said, the surface area. E is emissivity. Yeah, how much it's emitting, basically. It's usually from 0 to 1, if I believe. And C is the heat. Amazing. And yeah, I believe that's it. A 44-minute video of me talking about thermal physics. I'm gonna make a separate video of me just speed running through the questions. And yeah, thanks for watching. I hope this video is useful for anyone that watches this. And so sorry if I make some mistakes. If I made the mistake, please comment down, because again, I'm human. We're all humans. We're all bound to the mistakes. No one is perfect. No one is perfect, I don't think. Yeah, thanks for watching. And I'll see you guys again in another time. Bye bye.